Right, so before I get into the main results, I think it'll be easiest to cover the lower bound that it's based on, or that we built on, which is by my co-author Ryan Williams in 2011, which his main result was that NX is not in ACC, does not have polynomial size ACC circuits, which. So yeah, ACC circuits are constant depth circuits with and mod M gates for some constant M, which, to be honest, for this talk, it doesn't really matter other than the fact that it's a class that's really annoying to get circuit lower bounds for. So even for a giant class like NX, it was a pretty groundbreaking result to finally crack it. And so I'm going to cover the approach of how the proof works and then show how we improve it with our new paper. So the first part of it is taking a new satisfiability algorithm. So this AC0 D MSAT parameterized is basically just given a circuit with depth D and mod M gates specifically, if you have, for every possible constant, if you have a SAT circuit that runs for polynomial size circuits, so these are n-bit circuits with n to the k wires, if you can solve that problem in slightly better than 2 to the n time, then you get the lower bound. So that's this theorem A, that's the first part of it, and then the second part is Ryan explicitly gives an AC SAT algorithm that works up to 2 to the n of the epsilon circuits in 2 to the n minus epsilon, n to the epsilon time. And so the thing to notice with this proof is that there's a huge gap in between the efficiency of the algorithm and what's required to get this lower bound. And
it does more than
yeah, it does more than you want, than you need to get this NX lower bound. And so in fact, yeah, the limiting factor has to do with, or I'll get into that later, and that's in fact what we improve in order to get these lower bounds tighter, to where we can replace this NX with an NQP, and then we can also get something a little more general that works all the way down to NP if we have a more efficient algorithm than what theorem B gives.
So there's also a gap between n to the k and n to the epsilon sign?
Yeah, there's a gap for both of these. So it works up to circuits of this size running in that time, while you only need polynomial size circuits for the lower bound to apply.
And you don't exploit it, just
for the old proof, it doesn't exploit that, but our new one does. That's why we're able to get it tighter to where now this actually is the limiting factor. If we can get better, then we can get new lower bounds. So yeah, I put this in a chart because theorem A is what we're going to be changing now, or improving on. So in the original statement, we have theorem A it works for polynomial size circuits, and the runtime is slightly better than brute force, you save an n to the k factor, and you get a lower bound for nx. And in fact, one other thing to notice is this actually doesn't work just for satisfiability, but you can even get a gap SAT algorithm, and like I said before, this AC0 is not that important. Theorem A generalizes to any circuit class with just some very minor restrictions on it. But because we've got this algorithm for specifically ACC SAT, that's where we were able to get the lower bound, which is why it's stated that way. So yeah, the thing with gap SAT though is you don't have to just solve satisfiability. You just have, say you promise either, let's see. So if you have gap C SAT means you have circuits from this class C, which can be whatever you want. It could even just be polynomial size circuits. And you promise that whatever circuit you give, it's either unsat or over half the assignments are positive or are 1. So yeah, the probability that any input is 1 is at least a half. So like either nothing satisfies it or most things satisfy it. So yeah, if you can solve this, even just this gap set algorithm. Yeah?
Like a BBP, not like gaps. RP. RP. I mean, a gap set
Yeah.
actually mean that you have a bunch of clauses. And
Oh, sorry, it's,
most of them.
I meant not gap sat, but gap unsat. Or I don't know if that makes a difference, sorry.
No, but that's not right. The comment was that usually when I think the gap thing when approximation is that you have a bunch of clauses and you can either satisfy all of them or satisfy at most some fraction of them. This is different.
Yeah, this is, well, this is the opposite of either none of it's satisfiable or at least half. Well, I guess you could just like flip the output.
It's not what he was asking.
Or-
It's not-
oh, sorry.
They were just making a
very
point
different,
that this is not the usual what
Oh.
people in set solving are talking about
Oh, okay.
approximating. It's not about the number of clauses you satisfy, it's the number, the fraction of assignments
Right.
that are accepted. So it's more like looking for a heating set for an RP.
Exactly. Yeah, it's and so yeah, if you can solve this more efficiently, it like would provide a de-randomization of promised BPP, for example. So yeah, you only like you don't even have to solve full satisfiability to get these lower bounds. You just need like basically a gap sat algorithm, and then that'll give you new NP lower bounds. So now I'll just give a like the basic outline of the talk is going to be. I'll start with.
If BPP is equal to T, then you get this lower bound automatically. RP is equal to T.
I'm not sure if directly assuming P equals VPP would give it, because I think you do need, the gap sat algorithm in order to get this to work. But yeah, I'm not quite as familiar with that side. First I'll start with a proof sketch of theorem A, as well as basically why we were only able to get NX not an ACC before now. Then I'll get into the easy witness lemma, which is what lets us get around it and improve the results down to NQP. Like starting with the original statement of it, as well as then what we changed. And then finally, what allows us to prove this new easy witness lemma is kind of new MA circuit lower bound, which it uses the same technique as the old one, but we proved something slightly stronger that allows us to generalize this easy witness lemma. So yeah, now I'll start with theorem A. So for theorem A, we want to show that given a faster SAT algorithm, like for this circuit class, and the assumption that NX is in ACC 0. Oh, right. Sorry, I just realized I didn't state what these new theorems were. So yeah, before I get into that, basically the improvements, I'll call them A plus and A++, is we're able to get, if you have a 2 to the n of the epsilon like we have here, and the runtime is 2 to the n minus n of the epsilon, you can replace this with NQP. Doesn't have circuits of size 2 to the log n to the d for any constant d. And so yeah, NQP is this quasi-polynomial, like 2 to the polylog time. And we can also then further push it to if you have a gap sat algorithm that works for 2 to the epsilon n size circuits and runs in 2 to the n times 1 minus epsilon. So it's getting slightly bigger improvements over exhaustive search, but like proportional to the circuit size. Then with this one, we'd get NP doesn't have fixed polynomial size circuits, so n to the d for any constant d. So yeah, these are the new results.
Here there
of the size of the circuit?
Well, it's we only care about circuits that are this exponential size.
Yeah, but the runtime,
So-
when you say runtime to the n, is n there the number of variables?
Oh, n is the number of variables for the circuit.
Yeah, it's not the size
Right.
of the circuit.
Right, it's not the size of the circuit. Because, yeah, this is the circuit size we're solving for. So everything is in terms of the inputs to the circuit.
And the quantifier is like this constant d.
Yeah, it's for all d.
Some d.
Well, it's for all d that this holds. Like, that you can't put all of NQP into 2 to the n, log n to the d for every d.
The left-hand side has higher.
Right.
Yeah. Yeah, and with this technique, you won't ever be able to get the runtime bigger than the complexity class, just by how the argument works. Okay, so now we have trying to show we want to show that given a faster SAT algorithm and that NX Bazaine C, that we can actually speed up a non-deterministic computation. So you have something in time 2 to the n, and you want to put it in time little o of 2 to the n. Oh. Don't really need this anymore. But so yeah, we want to just contradict the non-deterministic hierarchy just by some small speed up. And so, so yeah, start with some language in this time class. And what we can do is just look at what is a computation like this look like. And you can break it into just 2 steps. You guess a witness. And that witness, because of the runtime, has length at most 2 to the n. And then you verify that witness. So you check that y is a witness for x in the same time period. And so if you want to improve the runtime, the approach taken is basically try to shrink both of these from big O to little o, so that if you can both get a witness that's smaller and verify it in less than 2 to the n time, you get your contradiction. So for part, and the basic way this is organized is the faster SAT algorithm allows us to do 2, and this assumption that NX is an ACC allows us to do 1. So we get smaller witnesses because of the upper bound assumption, and the faster SAT lets us verify it quicker. And so, first of all, let's see. I'll start with part 1 is covered by the easy witness lemma. And so, which is by Impagliazzo, Kobinetz, and Vigderson in 2002. So just informally, it's that if NX is in p-poly, then all NX problems have compressible witnesses. And so, and I'll write this out elsewhere, like explicitly what that means. Let's see, where should I? Want it somewhere to save because it'll be useful later. So we say like a class NX or even NP or whatever class you want here, you can say it has S of n size witnesses if for all languages in that class and for all verifiers for that language. So it's not just that like some verifier exists, but like every verifier has this property that for all inputs in the language, there exists a circuit of size S of n let's call it dx, just such that v of x and the truth table of dx. So if you lay out like all assignments to D in order, like just lay out the truth table, that is a witness for this verifier. And so basically, yeah, with this, we have that if nx was in p-poly, we have polynomial size witnesses. And so just to finish this off, in order to compress it, all we have to do is say, guess the dx from over there, which has polynomial size, and we can guess that in just poly n time. And so basically now we've gotten this little o for part 1 just from applying the easy witness lemma.
Poly n or with whatever size it is compressed to.
Sorry. Well, it's just because all we're doing is guessing the witness, and we know that this circuit dx is.
The end though. I mean, the size of dx is.
Oh yeah.
Whatever S of n. So.
Oh right. It's.
So poly S of n or something. Yeah.
I guess I stated it as S of n generally over there for when you say you have S of n size witnesses, but the easy witness lemma is if it's in p-poly, you have poly-size witness circuits. So yeah, I guess I should have said poly n size. But yeah, that's right. It's because we have poly n size witnesses that we have dx is poly-sized. And so now for
maybe it's worth mentioning an obvious conclusion of this is that nx would be in x. An obvious conclusion from having small circuits for nx is via this is that nx equals x.
Yeah.
Right.
Well, and it's even goes down to Merlin-Arthur time. You can solve it by guessing and verifying these.
Just making the point that a non-uniform upper bound implies a uniform upper bound. That's the beauty of it.
Yeah. Okay, and so now for part 2, I'm not going to get into too much detail because we don't change much from the 2011 result. But basically, for part 2, because we know this easy witness lemma works for all verifiers, you're actually able to, I guess for 2, you can just pick the verifier v such that a witness for x is equivalent to solving some circuit unsat instance. And yeah, it has to do with a problem succinct 3 sat, which, yeah, it's not that important to this talk, but basically, once you create this circuit unsat instance, we can then apply the circuit sat algorithm that we assumed exists. Yeah, so this faster sat algorithm allows us to verify that witness faster than this 2 to the n time, which then gives the contradiction. So yeah, I kind of rushed on that, but it's not quite important because what we want to focus on basically is part 1, because that's what we're able to get something better for. So now, so basically the limiting factor is because we have this fast sat algorithm, even if we had dx being or even if we were to try to shrink this nx down to nqp and np, like what we have in these lower bounds, part 2 actually still works. That because the witness size is shrinking too, like everything ends up working out pretty well. But the problem is the easy witness lemma originally only can work on nx. And so because that doesn't scale down, we have to start with like 2 to the n time and assume circuits about that. And so basically the way we get around it is to generalize this easy witness lemma. So now, yeah, we have a new easy witness lemma. Which is that, like we parameterize it, but like 2 easy ways to write it is, for example, if nqp has fixed polynomial, or is in fixed polynomial size, so it's in 2 to the log n to the k for some k, then you have that nqp has witnesses of size 2 to the order log n to the k cubed. And similarly, we can get, so that's 1, and then 2, we have if np is in size n to the k, so if it has fixed polynomial size, then we have that np has fixed polynomial size witnesses, so n to the order k cubed. And so with this, we're able to start instead with, like over here, instead of having nx, we can even put nqp or np in our circuit assumption, which then still gives us small witnesses, which we can then verify very efficiently and still get the contradiction.
So when you write the size, it can be size of basically any circuit class, not necessarily general.
Well, actually, when we prove the easy witness lemma, we prove it for general circuits. But with this assumption, you can have circuit eval is in ACC. So what you can do is take the description, which might be like polynomial size, and then just like apply one more layer in order to get the ACC circuits or whatever class you want. So yeah, we don't prove the easy witness lemma in terms of a specific circuit class, but it doesn't end up mattering for the argument. So yeah, with this new easy witness lemma, basically we're able to prove theorems A plus and A plus plus. So, and get around the limitations from before. So now I think I'll get into showing the proof of the easy witness lemma, starting with the original. So.
Maybe it'd be obvious in the proof, but I mean, is there a more general statement here, or is it like?
Yeah.
Okay.
Yeah, we parameterized it. I think you can kind of see that, like, if you have size S circuits for any class, you end up with like something like poly S of S of S of n. So like 3 compositions. So yeah, if you put a polynomial, that's k cubed, and quasi-polynomial, you cube it again. So yeah, it is parameterized, but it's easier to talk about for things like.
Figure out the general function for failing, so.
Right. Yeah, it took a while to get it just right to where it's not just a huge mess of trying to explain what's being said. So now, let's get into proving this easy witness lemma. So what we want is, let's start with the nx bin p poly. So rather than just talking about nx, but it's a little I'm going to talk about just time 2 to the n, if that's in size n to the k, which is for some constant k, that's actually equivalent to nx spin p poly, because you can just take an nx complete language to solve everything with fixed polynomial. So what we want to say is if you have that, then I'm going to simplify to a c, but I'll show that you can even get this order k cubed. Or, no, sorry.
So fixed is enough. I always fail to. So fixed is enough, but if you take a complete one, the reduction might depend on.
Well, the thing is, for nx, it's basically, I think when you pad for, once you get to exponential, like 2 to the n to the c, you end up with n to the c here. So it's n to the ck, so that's still polynomial. And then I think,
So you're saying you can do these things so that the reduction won't matter for the fixed size.
yeah, it's when you fix it to 2 to the n rather than 2 to the n to the c, then you can put it in fixed polynomial size.
This is a witness.
This is
But let's say this is a.
Okay, yeah.
You want to see how you want to see how this works.
Right.
So yeah, now we want to have that there exists a c for which this time 2 to the n has n to the c size witnesses. And so what we do is we assume the opposite, that it is in time class, but you don't have these witnesses. So yeah, assume the negation. That is in size n to the k, but then now we want to flip this statement over here. So the way you do that is just one step at a time. Or I guess, so yeah, it does not have n to the c size witnesses. And that means just negate all the quantifiers. So what we have is there exists some language in n time 2 to the n, and there exists a verifier for that language, and there exists infinitely many inputs that are in the language, but which don't have these n to the c size witness circuits, which means for every y, if the verifier accepts, then the circuit complexity of y has to be at least or greater than n to the c. Because if it were less, you'd have an n to the c size witness. So yeah, it's basically the negation of, if you don't have these size SFN witness circuits, it's like infinitely often you actually have a way to find a hard function, or at least to verify one. You can guess and check, assuming that you know these inputs x. You can then construct y in nondeterministic time. And so with this, the strategy is so basically we want to this time find small circuits for a provably hard language, like one that we know doesn't have. And so in the original, basically your hard language ends up just being a brute force, which I think this might not be the exact argument in the paper, but to make it comparable to what we have later, let's start with this language that's in P space. But doesn't not even infinitely often have size end of the case circuits. And so by that I mean that for almost every input length you can get this lower bound to apply. And it's just basically by direct diagonalization. You can just find a circuit of size, say end of the k plus 1, and go through all possible and find the lexicographically first end of the k plus 1 size circuit that does not match any size end of the k circuit. So you can verify point for point in P space, does this smaller circuit encode this function or not? And then you can do all that in P space and just get a hard function for almost every input length. And so, let's see. I guess here we go. So basically, starting with this hard language, it's in P space, and then what we can do is, like was mentioned before, with our assumption that we have nx spin P poly, which actually means that P space is in P poly, which actually then allows us to put P space into Merlin-Arthur time. So this is because P space is in P poly, and there's a Karp-Lipton type result that allows you to even solve it in Merlin-Arthur. So yeah, you start with this hard language, you can put it in Merlin-Arthur, and then from there we can actually then put it infinitely often into n times 2 to the n with n bits of advice, which I'll prove next. And then from here, we have this, even with n bits of advice, the circuit upper bound of n times 2 to the n is in size n to the k will still hold. So then you can put that in IO size n to the k, which we know can't happen for this hard language because we diagonalized almost everywhere. And so then that will give the contradiction. So now, I think this is the only inclusion that's hard to prove, I guess, for this. Which, so the way we do it is,
You want to guess? That's for you.
For me?
Yeah.
I'm actually trying to do the one before.
oh, that P space is in MA.
Given that so you assume that
This is just a Karp-Lipton argument. It's if you have the hierarchy collapses, right? You know the hierarchy collapses under this assumption. Well, it collapses up to MA. This is an easy thing to check, or easier. I mean, we have by now. Yeah. So that's it. No, you should guess. How do you eliminate random quantifier? This is easy for you. Yes. Yeah. So this uses derandomization. Yeah. Yeah. Let's see result about low bounded. This is derandomization. What's the source of the derandomization?
So yeah, that's basically it. Yeah, it's in order to de-randomize MA, you use these infinitely many inputs to get your hands on a hard function, which you can put into a pseudo-random generator, which then allows you to de-randomize. And because it's, you know that any valid witness is hard, it doesn't matter which witness you choose, it'll still allow you to de-randomize. And so,
The hard function for non-deterministic.
right, yeah, it only works for you need it still non-deterministic, but then because we assumed an upper bound for this time class, it doesn't end up mattering. We still get the contradiction. So yeah, you have I guess just to quickly put it into words, you have some end of the D time Merlin-Arthur algorithm. And so what you do is encode one of the bad inputs from for this language LW as advice, and so that's where the n bits of advice comes into play. And guess and check the bad y such that v of x, y accepts, and then use y in a pseudorandom generator that that fools n to the 2D size circuits, because then you can construct basically you can guess Merlin's message and then construct a circuit of size n to the 2D that takes Arthur's message as input, and then it just solves it. So then that would end up being the circuit you're trying to fool in this pseudorandom generator. And so then you can make that circuit to be of size n to the 2D. So as long as you can fool that, you can de-randomize this Merlin-Arthur algorithm. And so basically, the problem with this approach is that if we want to scale down to NP rather than NX, we no longer get that P space is in MA because we don't get P space in P poly. And so basically, yeah, that's why up until now it's been hard to compress down these results. So one way to try to get around that would be, let's see.
Is there a hard function? Is there a hard language? Use the function, use the P space because you find it hard in P space, right?
Yeah, it's because we found a hard language in P space. So now we have to take a different approach.
Down on hard languages, there's an old Cannon theorem that shows that even in the second level of the polynomial time hierarchy,
Right.
such hard functions.
And this is not enough somehow. So this is
Yeah.
not enough.
Well, I think. Well, yeah. The problem with that is, I think with those, they're not. You don't get this infinitely often. I think you have to go to the third, right, for that.
Yeah, it doesn't matter. Third level.
Although even with that,
So what would be the problem of using them?
I think the problem is the way. Let's see. I think maybe we could talk about this after, because off the top of my head, I'm not sure. Yeah. Yeah, I'm sure there's an answer. I'm just not thinking of it right now. So let's see. But yeah, I guess it's kind of with that approach that we instead use the MA lower bound. So this is by Santanam in 07. That MA with one bit of device is not in size n to the k. And so you can actually even mirror the argument there just by removing the p space and saying MA with one bit of advice is you could try to de-randomize that and put it in, well, now we're trying to generalize it to NP instead. So basically you can put Merlin-Arthur into, sorry, yeah, I guess it's if NP has size end of the case circuits. Let me, yeah, just if NP is in size end of the K and there exists that such that NP, so just, yeah, replacing it everywhere. So, yeah, now we have MA with one bit of advice goes to NP with n plus 1 bits of advice. So all you do is you include this bit of advice to solve the Merlin-Arthur as well as the input that lets you de-randomize. And then you can put that in, oh, I guess IO NP, and then that goes into IO size end of the K, which almost gets us what we want. But then the problem again is it only applies infinitely often. So from here, oh yeah, this might be where the issue came with before, because this approach almost gets it, but then you still have only infinitely often, which isn't a contradiction with this lower bound. Or, oh wait, no, wait, I guess if you went to, sorry, never mind. But yeah, I guess that it is a problem here that we only have IO, like that for infinitely many input lengths you get the lower bound, while the lower bound here just is that you have infinitely many inputs for which it doesn't have the circuits. So this isn't a contradiction yet. And so basically, this is where, again, we use a new like MA lower bound that's slightly stronger. It doesn't quite get this to almost everywhere. But like, I guess what we called it was an almost everywhere, where you can get it to where the lower bound applies often enough that you can still get a contradiction with this inclusion.
Just from that conclusion? Not from like a quantification of an IO or something like that?
Well, it does require a little bit of a quantification of the IO, that like you can apply the IO to inputs that are polynomially far apart. And so that's, yeah. So yeah, it has to be, we strengthen this IO just a little bit and we weaken, or I mean, we strengthen the lower bound a little bit to where they overlap and we can get the contradiction. So
what you're pointing out is that the p-space, the hard language in p-space is hard for every input, for example.
Yeah, for every input length.
You don't worry about the IO.
Exactly, yeah. Yeah, so like we know that that language is not even infinitely often having small circuits, so then if you even get infinitely often, you're done. So now I'll state the MA lower bound.
Just, we don't have to discuss it now, but I think that the Canaan result is also for every input length, basically. It's diagonal argument.
Right.
Works for every.
Yeah.
Language is constructed for every. Yeah, you just look at the circuit slightly bigger.
Yeah.
Log n bits, or k log n bits.
Yeah, off the top of my head, it seems like it would work, but I don't know. Like, there might be a subtlety.
Yeah, we'll review it at lab.
Okay. So yeah, here's our new Merlin-Arthur language. Is that you can say for any constant k, there exists a language in Merlin-Arthur with this time giving order log n advice instead of the 1 bit, such that for all but finitely many input lengths n, either, let's see, you have that this language, Merlin-Arthur language, restricted to n bits, like on n bit inputs, has complexity at least n to the k, or that this language on inputs of length n to the k has circuit complexity at least n to the k squared. So basically, the lower bound has to apply to either n length inputs or n to the k for all but finitely many input lengths n. So with this one, it's just, yeah, it's not quite getting it everywhere, but you can get it often enough that we can actually then use this de-randomization to still get a contradiction. And so,
Poly thingy.
yeah, that's where this is basically where the n cubed comes in, is like, we have to be able to de-randomize this, and like, which this Merlin-Arthur algorithm runs in about n to the k squared time on inputs of length n. And so we want to be able to de-randomize both parts with a single input. And so then, because yeah, for inputs of length n to the k, then the runtime would end up being n to the k cubed, which is where that n to the order of k cubed for the witnesses comes in. But yeah, that's, so yeah, I'll try to write that out so it's a bit more explicit, what I just said. Let's see. Just a quick, yeah, well, first I'm going to sketch how that allows us to finish the proof. And then, yeah, the last thing, if we have time, is I'll cover as much of this proof as possible. So yeah, but yeah, it's,
The other one.
okay. Oh, wait. There we go. So I guess I've shown what to do that with that. So right, to finish up the proof, what we do is let's say that L, we know it runs in polynomial time. Let's just say it runs in like Merlin-Arthur time n to the d for some d, which could depend on k or anything, which I'll get into that later when I prove the lower bound with order log n advice. So basically on input length n, we have an m to the 2d size circuit that takes Arthur's message as input. That is what we want to de-randomize. And we want it to work for both m equals n and m equals n to the k. So the largest circuit we want to be able to de-randomize is an n to the 2 dk. So basically, in our assumption, we had that, I guess if we're inverting it, we have that that's true for all C. So we can like choose whatever C we want to de-randomize. So you make it like C is order like 2dk, but like with the overhead of the pseudorandom generator. You want it to be able to fool n to the 2dk size circuits. So yeah, it's the pseudorandom generator fools n to the 2dk size circuits. And so then from here, now a single input x will de-randomize both length n inputs and n to the k length inputs. So then basically this, the inclusion up here, that NP is, or MA is in IONP, you can put both, like, you can solve it on both n and n to the k. And so the infinitely often is like stronger than just infinitely many, but like you can get infinitely many of these pairs n and n to the k. And so then the upper bound applies to those, and we finally get the contradiction with this new lower bound, that we can't have infinitely many n input lengths such that we have an upper bound for both. And so
what the number of the seed length of this PRG is something like n to the epsilon, where you can, right? I mean,
yeah,
That's where this like big O of the little C comes in, right? Like that high to the.
yeah.
oh yeah. Actually, it's that we can apply this for any. Oh yeah, sorry. Yeah, it's the seed length. Yeah, the seed length I think is n to the epsilon, right? Yeah, and that's right.
You have to gain something from the
Right. Yeah. Yeah. It's. Although you can also do some manipulations that like.
But this is what you later feed the the hypothetical sub-solver. The circuit you're creating, you're composing the PRG.
Right. Oh. Wait. It's.
Which circuit will be fed to the sub-solver at the end?
Oh, the circuit that's fed to the SAT solver.
Yeah.
I didn't really get into that. What it is like, you take the witness circuit, but then you actually. I think there's a function that like takes a witness, a small witness, and an input, and you construct a circuit around it that ends up being fed into the SAT solver, which I think that's a different part of the argument. Like you use a different. Yeah, I'm not sure if the PRGs here really apply to that side of the argument. But yeah, sorry, I'm not quite as detailed on that side.
Okay, it doesn't matter. So, but this side, you're just you're proving something stronger than the right-hand side, in that the simulation puts you not in time, in non-deterministic time to the end.
Right.
Actually in NP.
Yeah.
So what are you guessing and verifying that? This NPN plus 1 with this,
Well, it's
with this weekend.
well, what we have is like a witness of, say, some arbitrary polynomial size. It might be like much, much bigger, and that doesn't have like end of the C size circuits. So it's a polynomial gap between the length of the witness and the lower bound. So yeah, it's like the improvement doesn't come from making a stronger lower bound, but just rather shrinking the witness size so that the gap is still shrinking. So I think that pretty much covers the easy witness lemma. And so now the main thing left is to try to show this Merlin-Arthur lower bound. So
This is the improvement of the.
yeah, it even uses the same like basic approach as Santanam. It's just like showing you can get something a bit stronger if you loosen your restriction on the advice. So let's see. But yeah, it's basically the C, and like because D is about K squared, that's where we get the K cubed. But yeah, I'll get into that now. So, So yeah, I guess we start with, again, this hard language in p-space. Like, that's not in, or it doesn't have small circuits almost everywhere. And then we also have, this comes from, I think, Santhanan, like this and a few results before that. There's a special p-space complete language, LP space, with some extra properties. So first, it's p-space complete, like I said, which I think we'll mainly be using that for a reduction from this hard language to LP space. But then it's also paddable, so you can like adding or removing ones from the beginning of the string doesn't like change whether it's in the language. It's downward self-reducible.
Improving the news.
Oh yeah, this MA circuit lower bound, yeah.
And you still talking about p-space?
Oh yeah, it's going to be relevant because basically the Merlin-Arthur algorithm is going to try and solve these languages. So yeah, I'll get to that in just a minute. It's just, yeah, requires a little bit of, so yeah, paddable, downward self-reducible, and just informally you can guess and check these circuits, or circuits for this language, this LP space language, in Merlin-Arthur. So like, yeah, it has this special, it has to do with some other self-reducible properties that you can, yeah, random self-reducibility, as well as downward. Yeah, yeah, exactly. So yeah, because you have this like random self-reducibility, you can just guess the circuit and check that it like at least approximates it, and then you can solve the problem from there.
This is a permanent.
Yeah.
That permanent was p-space complete, and that's what you want.
Right, and so.
Downward self-reducible just means smaller inputs are easier? Or?
Well, that you can solve a given input given an oracle for smaller inputs.
Oh.
Like if you have an oracle for n-1 length inputs, you can solve it on n length in like polynomial time.
Sure.
So yeah, and the fact that you can solve it in polynomial time actually does become important for the proof too. But so yeah, it just, oh, I guess before I do that, I'll try to, I guess first of all, I'll define this L of n. It'll be, is just the largest input length m such that this LP space language on m bit inputs has like, let's say n to the ck squared size circuits. So basically you have this, that's basically the circuit sizes we're going to be guessing in this Merlin-Arthur algorithm, so that we want to be able to solve the largest possible p-space problem we can, where we can guess and check these circuits. So now the algorithm is fairly simple. It's just you take this L of n as advice. That's your order log n bits of advice. And what you do is, if L of n is at least n to the k, then you run this reduction to like you want to be able to solve this hard language. And so it's you've got this L hard instance ends up being about an n to the k size LP space instance, which I'm fudging the numbers a little bit for the talk just because it's otherwise it'd get annoying. But yeah, so if L of n is big enough to handle this reduction, then all you do is guess a circuit of size, or on inputs of length n to the k for LP space, and then you just check if R of x is in LP space. So you guess and check the P space circuit, and then you run the reduction and check if it's in the language. And you accept if and only if it's in the language. And so then otherwise now, if L of n is less than n to the k, you just try to solve LP space directly. So what you do is, or at least, yeah, if possible. So first, you depad the input x, or I guess, so you write it out as like some number of ones, a 0, and then let's say z. And if the length of this without the padding is greater than this L of n, so like if the input's bigger than what you can guess circuits for, you just reject. Otherwise, then you just check if this is in LP space, which it would be in LP space if and only if, I guess this is saying, is x in L hard, and this case is checking, is x in LP space. What? Right, I'm not really using that anymore, am I? Okay. So yeah, it's,
So what is this algorithm? You're going to prove a lower bound, right?
yeah, this is actually the algorithm for which we're proving the lower bound. This Merlin-Arthur protocol we can show doesn't have these circuits like.
Yeah, so when you say check, there's a reduction word or check between CSP. This is something that we can do because of the properties of this language.
Yeah, because of the properties of this P-space complete language, we can do all this. So yeah, there's a lot more detail that goes into this.
No,
but
that's a message. That's why this is.
yeah. So yeah, it's with this P-space complete language, we can then, so now I'll try to state what we're trying to prove, and then the proof isn't too involved. It's just, yeah, being sure to get everything completely straight. So what we're trying to say is, like we have this m of x, so we want to say for, I'm just going to say almost all to mean for all but finitely many n. So for almost all n, either L sub n has circuit complexity at least n to the k, which, so I don't get ambiguous with this LP space, I'm going to write it as a superscript instead. So on n-bit inputs, either it has the upper bound there, or you have the lower bound here on n to the k size, or length inputs. So we're going to prove this by contradiction, so we'll just assume the opposite, that basically we have small circuits for both, and try to get a contradiction from that. So I'm going to try and prove two simple properties that pretty much let this follow through pretty quickly. So we have for almost all n, if this L of n is at least n to the k, then L of n does not have small circuits, so it has circuit complexity at least n to the k. And so this actually, if you follow the algorithm right, this kind of follows pretty naturally that if you have L of n bigger than n to the k, you're solving this L hard, which we know doesn't have small circuits almost everywhere. So
This is essentially by definition.
yeah, pretty much by definition, we have that. But what's actually more useful is if you take the contrapositive of that, which makes it a little less obvious that if you have if you have n to the k size circuits, then your L of n has to be less than n to the k for almost all input lengths, which means that when you have small circuits, you have to be in the second case where L of n is n to the k and you're solving LP space. So now the second property, which then we have is for almost all n, if Ln L on n-bit inputs has an n to the k size circuit, then basically that L sub n has to solve this LP space language. So you can even say LP space on n-bit inputs has an n to the k size circuit. And so, yeah, this one takes a little bit more to prove, although it's actually an inductive proof. Like, first you show, like, for almost all input lengths, you have that LP space on, like, 1-bit inputs definitely has an n to the k size circuit if n is big enough, like almost all n. Because I guess LP space solved on 1-bit inputs, it's a constant size circuit. So for that one, it works. And then the rest is just inductively saying if it works for m-bit inputs, you can actually get it to work for m plus 1-bit inputs, all the way up to this n itself.
So this uses just a downward self-reducibility or random?
It uses downward self-reducibility, and it kind of implicitly uses the random self-reducibility in that it uses this guess and check circuit that you can do in Merlin-Arthur. The fact that you can verify that means that...
Like the uniform derandomization.
Yeah. So the proof for this is we have, let's just say, I guess it's for m equals 1, we have that LP space on 1-bit inputs has an order 1 circuit, or has a constant size circuit. So now what we want to do is say, like, if it works for just any m, like, I guess let m be strictly less than n. And we want to be able to show that if it works for m, then it works for n plus 1. So suppose that LP space on m-bit inputs has an n to the k size circuit, as well as L sub n as well. Like, both of these have n to the k size circuits. So, So then basically you start with this p-space language is in size n to the k. on n-bit inputs. So actually, we can use then the downward self-reduction to say that LP space on n plus 1 is in size n to the like 2dk for some, like if the reduction runs in 2 to the d time, then it's possible to, take this as your oracle, this end of the k size circuit, and you can construct a new circuit for m plus 1 bit inputs that's of this 2dk size, which is bigger than what we want. But what's important is that if this 2dk is less than then this like n to the ck squared, which you can just set c so that it has to be true, then this circuit can still be guessed by our algorithm M. And so what you do is like if you have these circuits, then you have that your L of n for these n-bit inputs has to be at least n plus 1. Because like just by definition, like L of n, if you have these circuits for size m plus 1, it has to work, or it has to be at least m plus 1. So then from here, we basically have that the language L sub n, or L to the n on input 1 minus n minus 1. So basically, if we pad the input so that this x is length m plus 1, and we're just adding padding to make it length n, this solves the p-space language on m plus 1 bit inputs. And so basically then, because this L to the n has size n to the k circuits, we can just use this circuit directly for L, this L, or language L, and just say LP space on n plus 1 bit inputs is in size n to the k. So basically, it's an inductive argument, but you end up in the same circuit every time. You're just saying that this language L solves p-space on, first it solves LP space on 1-bit inputs, and then you can prove with this that same circuit solves it on 2-bit and then 3-bit, and so on, and it actually goes all the way up to saying it solves p-space on up to n-bit inputs, which then you just run into the problem of you run out of inputs to add. And so there's not a contradiction yet. We use these two properties. Then basically what you do now using this is you assume n to the k bit inputs have circuit complexity at most n to the k squared. So then both of these, then you apply 2, and you can say that LP space on n to the k size inputs has an n to the k squared size circuit. But because of this assumption, what we're saying is if LP space has n to the k size circuits, n to the k squared for inputs of length n to the k, then your L sub n, or L of n, is at least n to the k for inputs of length n. So like basically, if you apply this point to inputs of length n to the k, you can then get that L of n has to be big enough so that this language, or this part 1 has to be solving L hard, which then we know from here that that can't be true for almost all input lengths, that it can't be solving your hard language. Otherwise, you'd get a contradiction earlier. So that's where the contradiction comes in. So it's like basically you're trying to force it to, like first you show that if you have small circuits, you can then solve p-space efficiently. And then from there, you use that small p-space circuit to solve a hard language. But it seems like you need it to separate it into 2 input lengths, which is why we only get the almost everywhere lower bound. And I couldn't really find a way around that, but this is still enough to prove everything else that leads to the NQP result. And so I think that pretty much covers it.
All right. Thanks.